Hello and welcome to the video lecture series on contact mechanics in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. And this is the third and last part of the third video lecture on contact mechanics algorithms, where you will learn how the total complementary potential energy can be used to formulate a variational principle-based algorithm for the contact mechanics problem. This video starts with an explanation of the total complementary potential energy, and then you will learn how this can be formulated mathematically as a variational problem. It will be discretized and you will see that it's a quadratic problem which, when solved, exactly fulfills the linear complementarity problem that we already know quite a lot about. Another very useful method to apply to solve the contact mechanics problem is the variational principle based approach that we will discover a little bit about in the following slides. This approach is based on the minimization of energy, and here we see the familiar strain-stress diagram for a linear elastic perfectly plastic material. And the UE here denotes the internal potential energy which can be obtained by integrating the stress curve from 0 to the point where the plastic flow starts. We can also view this problem in terms of the internal complementary potential energy, and we will soon see why. We note that, of course, the internal complementary energy and the internal energy are the same. So I think it's a favorable way of looking at the problem with the complementary energy, as it is actually the stress that causes, stress is the action that causes the reaction in terms of strains. So therefore it's more natural to view the problem from the complementary energy form. So the basic idea behind the algorithm that we will soon discover is minimization of total complementary potential energy. And it has two contributions. The first one is the internal complementary potential energy, and the other one is the virtual work. So the internal complementary energy is given by this expression, which we will see is actually a quadratic expression in P, and we will derive it. And the virtual work is just given by this expression, and it represents the work caused by forcing the system into a state with equivalent virtual displacements as you have for from the applied loads.
Let us consider the contact between two half-space bodies, namely the one depicted here, with an elastic upper body with a lower boundary described by G, and a rigid lower body with a perfectly flat upper boundary coinciding with the XY plane. Then we know that if we load the deformable upper body against the lower rigid one with the force W, or equivalently, if we just apply a rigid body movement delta, then the elastic body will deform. And here we can see the deformation U, which is given by this expression of Boussinesq's type. Moreover, there will be a pressure distribution resulting from this, and actually, since the system is in equilibrium, the load contribution by the contact pressure must balance the applied load, and we have the following force balance equation, where minus W, since W acts in the negative z direction, is counterbalanced by the integral of the pressure over the whole domain. And this gives us our equilibrium equation. Okay, so in order to obtain an expression for the internal elastic energy, we will start by considering the pressure at one point in the xy plane as the cause of the effect in terms of the elastic deformation U. Then we will postulate here the expression for the elastic energy in terms of the elastic surface energy UE prime at a point in the xy plane. And note here that the elastic surface energy has the unit Newton meter over area. And we can therefore obtain the internal elastic energy by integrating over the whole domain omega. At each point in this xy plane, the elastic surface energy is given by integrating the pressure over the distance of deformation. So the integral of P from node to U du prime. Now we have to be a little bit careful here because of the linearity. P and U are linearly related. And if we name this constant of proportionality between U and P, we can replace P in the integral for the elastic surface energy with Cu, or Cu prime, since U prime is the dummy variable. So now we should integrate Cu prime du prime from 0 to U, which is easily done, and we just get Cu squared over 2. However, by means of the linearity between P and U, we can reformulate Cu squared over 2 as Pu over 2, as you see clearly here. And this means that we have obtained the expression for the internal elastic energy precisely as we set out to do. Now, the virtual work part. So consider the situation that we had initially, okay? And let us consider the initial position of the boundary of the rigid counterbody as the reference plane. Now, in fact, this is the xy plane, and we will use it to formulate the undeformed gap between the surfaces G. The virtual work is the energy required to impose a displacement on the boundary of the deformable body that renders exactly the deformed body that results or resulted, as we saw when we applied the force W, which we did before. So let us denote this imposed displacement by u star, and it is of course a function of x here. By complementarity, we have p greater or equal to 0 and u star plus g minus delta equals 0 inside the contact zones. And this means that we have an expression for the imposed displacement u star, which is just delta minus g inside the contact zones. Outside the contact zones, p is 0 and u star plus g minus delta must be greater than 0. Well, that means that u star is greater than delta minus g outside the contact zones. But a key ingredient here is that p is 0 there. Now, the surface energy can be formulated directly as the product between the imposed displacement u star and p. Well, similarly as work is force times distance. Okay? But now, due to that we have the complementarity here, we have that when the pressure is greater or equal to 0 in the contact zones, we can formulate, we get a non-zero expression for the surface energy, which is delta minus g times p. And otherwise it is 0. And therefore, since surface energy integrated over the whole domain gives the energy, we have that if we integrate uv prime as defined here above, we get delta minus g times p as the integrand. And if we just negate that integrand, we have arrived at the desired result.
Okay, summing up on the total complementary potential energy approach, we now know that we can compute it by means of this expression we just derived, but we also know that the applied load is given by the integral of the pressure over the area where it acts. Let's denote this by W as we've done before. Then we can restate the total complementary potential energy V star of P like this. And this will be useful in the following. So the virtual work can be computed like this, and we know that the gap between the surfaces is defined by just the upper surface minus the lower surface, and delta, color in orange here, is the virtual rigid body movement. We have U being the deformation, the difference between the deformations of the upper minus the lower surface, and P is the contact pressure. So solution to the contact mechanics problem is then obtained by minimizing this total complementary potential energy, subject to the pressure must be positive or equal to 0 everywhere, and we have also the load constraint. So the applied load W must equal, of course, the pressure integrated over the whole contact area, or the whole nominal contact area, I should say, and G is to be regarded as an input parameter. I put this is quotation marks here because it's a function, but still it's input. W is input, pressure is a dependent variable, and U is a dependent variable. We recall that the Boussinesq's equation defines the deformation, or the relation between the deformation and the pressure, and we can therefore, of course, insert this expression into the equation for the total complementary potential energy. And if we do now for a 3D half space, we have the kernel looking like this, colored in bold X, because with this I mean X, comma Y, of course. And then if we insert it into the total complementary energy, we get this expression, which if we formulate it discretely in summation notation, it can be written like this. We can also formulate it in matrix vector notation, which is quite convenient when we then minimize our total complementary potential energy with respect to P. So doing that, we know that finding the minimum value is equivalent with finding the gradient of our function with respect to the independent variable in this case, which is P for the total complementary potential energy, and set this gradient to 0. Find where the places where this gradient is 0, and since we have this simple matrix vector notation, it's very easy to see that if we differentiate this one or take the gradient of this one, we obtain exactly this expression reading Kp minus G equals 0. So finding this minimum value can be done by means of many different minimization algorithms, and the simplest one is the steepest descent method. So it just look for the steepest slope at a certain point and takes a step in that direction, and then looks again for the steepest slope and takes a new step in that direction and iterates this until it ends up at a local minimum or hopefully a global minimum. We also note that Kp is just U. It's a deformation U in matrix vector form, and when U minus G is 0, we have contact, because that's exactly the definition. It's the complementarity definition. So the total complementary potential energy is not correct without the force balance. And we can compute or can find force balance by taking our initial pressure, considering only the positive parts, integrating this to obtain an initial value for our applied load. Okay, we can then check if this is correct. Well, then we're done. Probably it is not, and we can apply a shift on our pressure distribution, either up or down. If the initial is less than the applied load, we should of course shift our pressure up by an amount alpha. Doing so, we need to reconsider the contact zone, or the sort of virtual contact zone where the pressure is positive, and we re-evaluate the integral of the new pressure, which is shifted by an amount alpha, we get a new applied or new load contribution from the pressure, and we can test if this one is equal to the applied load. If it is, well, P is P nu, and we're done. We have found the solution P nu, which minimizes the total complementary potential energy and satisfies the force balance. Also, P is positive everywhere. So the flow chart of the solution procedure may be viewed in this way. So we start by defining the gap between the surfaces. So this is, of course, now the input. And then we have an initial guess of our pressure, and we take this as a uniform initial guess, meaning that we average the load over the nominal contact area, and if it's in dimensionless form, it's just this number. And then we calculate a new pressure by adding to the old one the gradient of our total complementary potential energy evaluated at the old pressure. But here we also know that this gradient is exactly the elastic deflection evaluated for the old pressure minus G at the contact zone, at the contact spot. So we can pose our new pressure in terms of the deformation, Boussinesq's deformation, which we can compute, and the input function, which is the gap between the surfaces, G. Then we carry out the force balance iteration, 7 force balance iteration, by shifting the pressure up and down with an alpha until we find the alpha that summed with the pressure actually integrates to the applied load. When we're ready, and we can truncate the pressure, truncate all the negative values from the pressure, and then to test whether we have solved the problem or not, we check if all our contact points lies sufficiently close to a contact plane. So we measure this by taking some kind of measure of the deformed gap. It could be the maximum distance found in all over the contact zone to a plane, or it could be an average distance if you like. But if you take the maximum, you really obtain a very precise result for the complementary potential energy, and of course this tolerance epsilon must be calibrated to your system at hand. So if we are down at the micrometer level, it can have certain value, and if we go down even further, it must be made even smaller. Of course, we can make it relative also. So there are many ways of posing this, but this is the convergence check. And then typically we're not really done. We're not satisfied. At least we're not satisfied if our measure of the distance from this contact plane of the contacting points is too large. We must set our P old to be P new, which we just have found, and we reiterate over and over again until we're done. So this total complementary potential energy leads to this variational principle based problem formulation, and we have some certain very important properties of this one, and it's that it's a quadratic form. It is supported by all rigorous mathematical foundation, and one of the most important features there is that we have a guaranteed uniqueness of the results.